Let's go to the chapter 5, estimation. There are 3 goals in this class. First one is no numerical notations. Second one is no significant figures. And the last one is understand the differences between repeatable, accurate, and precise. Okay. Sometimes, most of the case, engineers will be faced with solving problems using limited informations. We don't know true values. For example, automotive safety. We are using crash test dummies in order to understand impacts on a driver. But how we put the 5th percentile US male dummy inside the vehicle more realistically, like a real human? Okay? We need to understand how real humans sit inside the vehicle. But the sitting position is varied depending on person to person. In this case, we need to estimate how 50th percentile US male driver sit inside the vehicle. Another example is that how to determine the location of buttons on mobile phone to have a better reach, better access when people are using the phone in one hand. Okay? How to determine the location of the button. We need to estimate the positions. When I was in the University of Michigan, my supervisor, Dr. Matt Reed, he asked me to develop statistical models to predict a driver's hip and eye locations. And the models should express 4 significant figures. So we measured 90 US drivers' driving postures and quantified 7 joint locations on the body while they are driving. Okay. And then the models were developed by employing regression analysis. And we published these models in human factors journals. As you can see that the statistical models have 4 significant figures. And some numbers are expressed in scientific notation. You can see the T12L1Z joint location prediction models have scientific notations. Why and when we need to use notation? Think about the age of Earth. I searched it through Google, and Google tells me that it is 4.54 billion years old, and it has plus minus 1% error. The question is why the Google expressed that number like 4.54 billion or 4.54 times 10 to the 9th power. Why not just spell out this very large number or very small number? The reason is that providing better readability for readers. And of course, we don't want to miss any 1 or 2 zeros in the numbers when you write the number. There are 4 types of numerical notations: standard, scientific, engineering, and calculator notation. The standard is just a standard. It shows number without any times 10 or e. Scientific notation is using a power of 10 times a value. Look at this format. m times 10 to the nth power. In scientific notation, the absolute value of m should be more than equal 1 and less than 10. Then, what is engineering notation? Engineering notation is one of scientific notation, But the difference between scientific and engineering notations are that the superscript number in engineering notation should be multiple of 3, and the absolute value of m is more than equal 1 and less than 1000. Okay. Many of you may not be familiar with engineering notation. Engineers often use SI prefix, such as kilo or mega, to avoid long strings or long strings of zeros that are difficult to read. So engineering notation is specifically designed to make it easy to recognize the appropriate SI prefix. The last one, calculator notation. We call it E notation. You can easily see this format on your calculator. E stands for exponent. The E means times 10, okay, to the nth power. Here are examples of SI prefix. If you look at the kilo, kilo is 10 to the 3rd power. How about mega? Mega is 10 to the 6th power. Minus is also same. Okay? It's multiple of 3. So remember, in engineering notation, the superscript number are multiple of 3. Now let's practice. Could you express this number in scientific notation? You have 20 seconds. Let's start. Alright, let's see together. In order to express this number in scientific notation, we need to move this decimal point to the right, backward. So 1, 2, 3, 4, 5, 6, 7, 8. We moved 8 places backward. Okay? So the answer is 9 times 10 to the negative 8th power. Then let's practice the number in engineering notation. You have 10 seconds. Start. Let's see together. In order to express this number in engineering notation, we need to move the decimal point to the right, as we did in scientific notation. 1, 2, 3, 4, 5, 6, 7, and 8. Can we stop here? No, because 8 is not multiple of 3, so we have to move one more, 9. Okay, so we moved the decimal place 9 places to the backward. So the answer is 90 times 10 to the negative 9th power. Let's finalize understanding the differences between scientific and engineering notation. Here are numbers in standard notation. In scientific notation, as you can see, the format is m times 10 to the nth power. The range of absolute value of m is less than 10 and more than equal to 1. In engineering notation, as you can see, the format is m times 10 to the nth power. but the superscript number is multiple of 3. Okay, the range of absolute value of m is less than 1000 and more than equal to 1. A couple of common pitfalls in scientific formatting are shown. Remember, the format is m times 10 to the nth power. The absolute value of m should be in more than equal 1 to less than 10. So in this case, we have to change this 59,800 to 5.98. Negative are same. So absolute value of the m should be higher than 1. Okay. Second, do not write calculator notation using capital E with a superscript number. Okay, here it looks weird. So do not superscript the power. Okay. It looks like in this case it's a worst case. Even worse is using lower e with a superscript. Since this looks like the constant e, which means 2.7 natural logarithm to the 9th power. So it looks weird, also weird. So change e to the capital E and 9, not superscript 9. Okay. Now what is the significant number? The significant number is the digit considered reliable as a result of measurement calculation. The meaning of significant is all digits other than 0. All digits other than 0. But there is exception. 0 is significant when it appears between two non-zero numbers, such as 306, 306 has 3 significant figures. So in this case, 0 considered as a significant number. 5.006 has 4 significant figures. And also, if it is a terminal 0 in a number with a decimal point. So in this case, the significant figures are 4 significant figures, not 3. So 0 is considered as significant because it is finished as 0. How about 2000.0? It has 5 significant figures. Okay, 0, the number is ended with 0. So this 0 considered as significant figure. So again, significant figures is not same as the number of digits and number of decimal places. Here is an example. The number 376, the decimal point is here, okay, 0. It has 3 significant figures, 376. How about this one? As I mentioned previously, if the number with a decimal point, if it is ended with 0, then the significant figure is 4. The 0 is considered as significant number. The decimal place is 1. How about this? Decimal place is 0, and this 0 is also considered as significant number. So 6. How about this one? This one, there is no decimal point. So decimal point is 0, and even though it is ended with 0, but there is no decimal point, in this case 376 is significant figures. How about this one? Decimal point is 7. 1, 2, 3, 4, 5, 6, 7. Okay, How about significant figures? It ended with 0, with decimal point. So in this case, 5. Here, no decimal point, 0 decimal place. What is the significant figures? 3, 7, 6. Here, this slide, I want to explain the difference between accurate, repeatable, and precise. Before we can determine if our answer is repeatably precise, we must understand the definitions of accurate, repeatable, and precise. As you can see here, accurate is a measure of how close a calculation or measurement, or an average of a group measurement, is too close to actual value. For example, you can see accurate, these 5 points. The average is close to the target. Okay. How about this one? It's very close to the target. It's accurate. How about repeatable? Repeatable is that how close together multiple measurements. Alright? So you can see this is very repeatable, but this is not repeatable. This is not repeatable, and this is not accurate. This is also not accurate, but repeatable. The precise is the combination of accurate and repeatable. Okay, so the precise is reflected in the number of significant figures used to report a value. So that means the more significant figures, the more precise the value is. This table shows the measurement from 3 probes used to measure the temperature of boiling water. As we all know, in this case, the true temperature of boiling water is 100 degrees Celsius. Okay, true temperature is 100 degrees. Note that the 3 measurements from probe 1 are close together. Okay, which means it's repeatable. But the average of these 3 measurements is not close to the correct value. So this is not accurate. This is repeatable but not accurate. How about second one? The average is very close to the true temperature, right? So it is accurate, but the individual values vary considerably. Okay, so this is not repeatable. How about probe 3? Repeatable, accurate. The probe 3, the average of 3 measurement is very close to 100, so it means accurate. And also, if you look at the individual values are very close to each other, so it means repeatable, accurate and repeatable. In this class, we have learned 4 types of numerical notations: standard, scientific, engineering, and E notation. And we know what is significant figures, and we know the differences between repeatable, accurate, and precise. Thanks for watching this video, and have a good day. See you this Thursday.